Welcome to a lesson with Dr. Pal. Let's take a look at another example of showing whether or not a series or an integral converges or diverges based upon an asymptotic inequality. So suppose that we have a series like this, like n goes from 5 up to infinity, and we have something like n. Let's see, let's suppose we have something like n cubed plus n squared minus 1, and all of this is over, let's see, all of this is over n to the, so n to the fifth, and so n to the fifth, and suppose we have something like n to the fifth minus n. Okay, let's look at this and see, does it converge or diverge? Now, right away, rule of thumb, if we just ignore everything but the leading terms, we get n cubed over n to the fifth. Now, notice that this is a lot like saying n 1 over n squared. Now, what do we know about 1 over n squared? By a p-test, p is equal to 2 in this case. This actually, or like the integral on this side, this converges. Since the integral converges, the series will also converge over there. So we know we want to compare this to something to show it converges. That means we'd like to compare it to something small, to something else. So this might be smaller than it. So let's try that. Suppose it's smaller than 1 over n squared, or some multiple of it. If we can asymptotically show this, then we've shown that this converges, since it's smaller than something we know converges. So we need to develop this inequality. Okay, so we need something that's eventually bigger than this in the numerator, and that would just be 2n cubed. We just double the leading term. That's a plus this over here, and eventually this is bigger than that, so that works. And on the denominator, you always reverse the inequality, so something smaller than this looks like 1/2 of n to the fifth, since what we're subtracting eventually is smaller than 1/2 of n to the fifth, so we can just say 1/2 n to the fifth. So we get a constant here. All right, and this will look like 4 times 1 over n squared. So we have just shown that this is smaller than something that we know, when put into a series, would converge. Therefore, this also converges. Now keep in mind, this type of comparison assumes that everything is positive here in our terms as we move along, so that we can actually make this comparison above the x-axis and make it work. So this is really, these comparisons work for the idea of absolute convergence. Absolute just meaning absolute value, positive. So absolute convergence and divergence. Thanks for watching.